Hi, Assalamualaikum. My name is Intan Nusyaira binti Ali Rozi and my metric number is 2023184737. I will begin our group presentation with the introduction. George Green, a British mathematician and physicist, introduced Green's theorem in 1828. Green's theorem relates a line integral around a simple closed curve to a double integral over the plane region bounded by that curve. It's a fundamental concept in vector calculus, often applied in vector fields of a plane. Green's theorem allows conversion of a complex line integral into simpler double integrals and vice versa. It finds applications in physics for solving two-dimensional flow integrals and in plane geometry for calculating area and centroids of plane figures.
We proceed to the first case study 1. Sarah and her husband just got married last week and moved to the new house, and last weekend they went to IKEA to buy a mirror for their bedroom. The mirror that they bought is the upper semicircle with equation x squared plus y squared equal to 9 and the x-axis part. Calculate the equation of the mirror where fxy equal to negative 2xy squared plus exi plus 2xy squared plus cos yj using Green theorems. So this is the image of the mirror and the graph of the semicircle that we get from the mirror. Next, we proceed to the mathematical calculations for case study 1. P is equal to negative 2x squared y plus ex and Q is 2x y squared plus cos y, and Py is equal to negative 2x squared. Qx is equal to 2y squared. Then, from the x squared plus y squared equal to 9, we will get the radius of 3. And then, we proceed with the formula double integral qx minus py dA. And then we get 2y squared minus negative 2x squared dA, and we factorize 2y squared plus x squared dA. Next, we will get 2r r dr d theta with the upper bound of dr 3 and lower bound 0, d theta, upper bound pi and lower bound 0. And then we get r squared dr d theta, and then we integrate the r squared. We will get r cubed over 3, and then we substitute 3 into r, and then we will get 9 d theta. After that, we will integrate 9 and it will become 9 theta, and then we substitute the value pi and 0, and the final answer will be 18 pi.
Firstly, we start with comma restart followed by with linear algebra. This is used in the context of preparing and setting up for linear algebra computation. In other words, before we start to run everything, we must have a restart command. Next, command with vector calculus. This command loads the vector calculus package in Maple, which provide tool for performing vector calculus operation. This package include function for working with vector field, and operation such as gradient, divergence, and line and surface. After that, we use command with plot. This is used for creating 2D and 3D plots in the Maple. Next, the Maple command implicit plot x squared plus y squared equal to 9, y equal to 0, x equal to negative 5 to 5, y equal to 0 to 10. Plot the curve defined by the equation x squared plus y squared equal to 9 and y equal to 0 with the specific range for x and y. Here, the equation represents a circle with radius of 3 centered at the origin. However, since the y range is 0 to 10, only the upper half of the circle, which is a semicircle, will be visible. The equation y equal to 0 corresponds to the x-axis, and it will be displayed as a horizontal line across the specific x range from negative 5 to 5. This plot visually shows the upper half of the circle intersect with the x-axis. Next, we move to the command fill plot negative 2x squared y plus exponent x, 2xy squared plus cos y, x equal to negative 4 to 4, and y equal to negative 1 to 2. This command generates a visual representation of a 2D vector field over the specific range of x and y. Here, the equation defines the x and y component of the vectors at each point in the plane. The plot displays arrow at various points within x equal to negative 4 to 4 and y equal to negative 1 to 2, where each arrow shows the direction and magnitude of the vector at that point, illustrating how the field behaves across the region. In this mapper, the command defines two functions which is p and q, and then we find their partial derivative. P is given by negative 2x squared y plus exponent of x, and q is 2xy squared plus cos y. The command differentiate py compute the partial derivative of p with respect to y, which is we get negative 2x squared. And for the command differentiate qx, compute the partial derivative of q with respect to x, so we get 2y squared only because cos y is constant. Last but not least, after all the command is derived above, so we can use Green theorem. In Green theorem, we use double integral which is qx minus py, so we define it as capital M equal to n minus m. Because the plot we get is semicircle, so we use a double integral in polar coordinate. It defines a function n equal to 2r squared to integrate over a region where r range from 0 to 3, which is the radius, and theta range from 0 to pi. So we integrate it and we substitute the value, so we get the answer is 18 pi.
Next is case study 2. The problem statement in case study 2 is the company Tan Lifasha Perfume Inc. is introducing Elegance, a new premium perfume bottle brand. Their goal is to create a distinctive and refined bottle form that optimizes the available space in the packaging while maintaining aesthetic appeal. This company decided to make a perfume bottle with elliptical equation of x squared over 25 plus y squared over 16 equal to 1. To guarantee the best possible form for the perfume bottle, the design team used Green theorem to compute the area of an ellipse. This is the figure of the perfume bottle and the graph that we get from the elliptical equation. Now, I will explain the mathematical calculation. Firstly, we define x and y using the parametric equation. Then, we differentiate x and y. After that, using the Green's theorem with the vector field of the ellipse, which is p equal to negative y over 2, q equal to x over 2. Differentiate p with respect to y and then q with respect to x. Then substitute into expression qx minus py, we get 1. And then convert the line integral into a double integral dx dy. Since the region is an ellipse, we integrate it with respect to x and y. The limit of integration is a 0 to 2 pi, and then subs x and dy. Integrate like usual and we get the final answer is 20 pi.
By using Mapple, we can also find the solution to this problem. Firstly, we use with student vector calculus, which means we are loading the vector calculus sub-package from the student package. Next, with plots means to load the plots package, such as to generate 2D and 3D plots. Then we use implicit plot to create a graph. We use implicit plot because it defines a relationship between x and y. In this command, we put the equation x range, y range, and options like color and thickness of the graph. Then we use fit plot to visualize how vector fields behave over a region, providing insights into their direction and magnitude at various points. Then we insert our p, q, m, n, and x, y with their derivatives. To perform the integration, we use I and t, int, which represents an unevaluated integral. I and t is we combine multiple integrals before evaluating them and apply simplification. Lastly, we use a value to evaluate the expression. Another method is that we can find the solution by using the flux formula by defining fr and using a simplify command to get the integration form, then use the flux command to get the result of the problem.